So it says it's recording, right? Or it's about to start. Okay, good. So now we're going to start chapter 21. This is the last of the monster chapters. So remember 18, 19, 20, 21. These are the biggest chapters. And you'll see that in this chapter, chapter 21, we're dealing with alpha carbon chemistry. And we're talking a lot about enols and enolates. There aren't as many reactions as chapter 20, even though there are quite a few, but there's quite a lot of connecting carbons in this chapter. And that's what students find most challenging. And so I'm going to try to go over that with you in detail, well, especially once we get into section 21.3. So let's get started by defining enols, enolates, and alpha carbons. So it says Greek letters are used to describe the proximity of carbon atoms relative to the carbonyl group. And we're going to see this. We're going to talk mostly about the alpha carbons of aldehydes and ketones, but we'll also talk about alpha carbons of other compounds like carboxylic acids and esters. But again, if we have our carbonyl, we don't give a Greek letter to the carbonyl carbon. So I mean this carbon that I'm putting in the blue circle, it gets no Greek letter. But going one carbon away from that, we have an alpha carbon, right? And it wouldn't matter which side. Then we have a beta, then gamma, so on and so forth. And what we're going to focus on in this chapter is we're going to focus on the chemistry that occurs at alpha carbon. So alpha carbon chemistry is what we're going to focus on. And something that you have seen a few times in this class is an enol. I introduced that to you even way back in Organic Chemistry 1. And it says here that alpha protons are the protons attached to an alpha carbon. Okay, so if we have an alpha carbon, let's just label this is an alpha carbon, this is an alpha carbon. So all of the protons that are attached to that alpha carbon, and in this molecule, which is acetone, there are 6 of them, those are all considered alpha protons. So alpha protons attached to the alpha carbon. And it says here that most reactions covered here proceed via an enol or an enolate intermediate. And so what happens is that if we take our ketone or our aldehyde and we treat it with a catalytic amount of acid or base, what we end up getting is we end up producing an enol, which you would remember is a tautomer of the ketone or aldehyde, right? A tautomer just differs in the placement of a pi bond and a proton compared to the original ketone or aldehyde. But what we're going to see a lot of as well is if you take a ketone or aldehyde and you treat it with a strong base, is that you can remove an alpha proton. So if I just go ahead and I delete all of this, okay, and I'm just going to draw in one alpha proton like this, just for instructive purposes here. If I take a strong base, okay, and we'll just imagine some kind of generic base like this, then I can abstract that proton, right, and make what we call an enolate, right? So you have an enol, which is uncharged, and then an enolate. And you remember from all the way back in General Chemistry 1 that whenever you have something that ends with ate, sulfate, carbonate, nitrate, it has a negative charge. And again, most of the reactions that we're going to look at in this chapter are going to proceed via an enol or an enolate. So let's get back into the enol. And it says here, in the presence of an acid or a base, a ketone or aldehyde actually exists in equilibrium with an enol. So if we have a ketone, just a simple ketone like acetone, right? This is the simplest possible ketone we can have. It's always going to exist in equilibrium with its enol. Now, most ketones are going to prefer or lie to the side of the ketone in the equilibrium. Now, keep in mind, this is not resonance, right? This is an actual equilibrium. And if you're wondering, well, what if I got rid of all the acid or base? Could I then, prevent the tautomerization from occurring? The answer is it's very difficult to do that, extremely difficult to do that, because any kind of glassware is going to have a little bit of acid in it, just by virtue of the fact that it's glass. Anyhow, I won't go into the details of that, but suffice to say that most ketones are going to favor the ketone form, and the enol form will only exist in a very small amount. And again, remember these arrows, that means these arrows and these arrows, these are not resonance arrows, right? These are equilibrium arrows. I just want to remind you of that as we move forward. Now, there are exceptions to the rule, right? There are some compounds where the enol form is actually preferred. And an example would be this 1,3-diketone. So if you just number, and this isn't using nomenclature rules, if you just have this 1,3-diketone, sometimes we call this a beta dicarbonyl, right? You have the alpha carbon here, and this is the beta, right? So beta dicarbonyl. Either way, this 1,3-diketone, you can see that the enol form here, so this is the enol form, it actually is favored at equilibrium. And you can see why that is. There's actually two reasons for it. Number one is that when you have the 1,3-diketone existing in its enol form, it's stabilized by conjugation, right? And you remember that conjugation is when we have double bond, double bond like that. And then we also see that there is an intramolecular hydrogen bond that is formed between this carbonyl oxygen and the hydrogen of the enol. And so we have two factors that are contributing to the enol existing preferentially in equilibrium here. Give me a thumbs up if you follow me on those two. The fact that the conjugation, right, and we talked about how there's stability in conjugation, and then the hydrogen bond also has an effect there as well. Well, there's one more example of a compound where we see the enol form vastly preferred or vastly favored over the keto form, and that would be phenol, right? Everybody knows this compound. You've seen phenol many, many times. So this is phenol. You had to learn the name of this compound way back in chapter 18, maybe before that, as a matter of fact. Anyhow, you can see that phenol actually is an enol, right? There's an enol in the compound, and you can imagine why that the enol form is so much greater or so much more preferred than the keto form. Well, it's because this form is aromatic, right? This is aromatic, and you know there's an inherent stability with a compound that is aromatic. And over here, this compound is non-aromatic, so non-aromatic, right? We have an sp3 hybridized carbon here, and so we don't have a continuously overlapping system of p orbitals. So again, a very specific example, phenol, but you do have to know the 1,3-dicarbonyl. So you got to know the 1,3-dicarbonyl, the enol form is going to be preferred. You have to know why. You have to know phenol, that the enol form is going to be preferred. You have to know why. And now we're going to get into the mechanism of the conversion of a ketone to an enol form. And we said, and I'm just going to back up here. I hate to back up too much in my slides, but you might remember that it said this can be done in a catalytic amount of acid, or it can be done in a catalytic amount of base. And you need to know both of these mechanisms. You need to know the mechanism for the conversion of a ketone to an enol in acid, and you need to know the mechanism for the conversion of a ketone or aldehyde to an enol in base. The good news is both of them are just two proton transfers is all it is, and a little bit of drawing resonance structure. So let's start by taking a look at the mechanism of the tautomerization in acidic conditions. So like I said, all it is two proton transfers, right? Proton transfer, and a little bit of resonance work here. So the first step is going to be to protonate the carbonyl oxygen to render it more electrophilic. And then what happens is we end up drawing a resonance form here where we move the positive charge from the oxygen to make a carbocation. And then we do a proton transfer where water comes in and behaves as a base, and we end up with our enol form. And again, I can't stress this enough, you have to know this mechanism, okay? You have to know the mechanism of tautomerization in acidic conditions. And the good news is the mechanism in basic conditions is just a couple of proton transfers as well. First step is a proton transfer. Now, if you look at these two forms of the resonance hybrid of the enolate, right? So here's our enolate. I mean, technically, I guess this would be the enolate because it's got the alkene in it. Anyhow, that's neither here nor there. But you notice that there's one that has the negative charge on a carbon, and so that's the first one. And the second one has the negative charge on the oxygen. If I call this one A and I call this one B, does anybody know which one of these would be preferred? Which one of these would be the greater contributor to the resonance hybrid? And it's not a trick question or anything. Yeah, okay. Yeah, somebody said B. It should be B, right? Because the oxygen is bearing the negative charge and oxygen is more electrophilic. All right, yeah, absolutely. But if we look at the electrostatic potential map, what we see is that, yes, there is more electron density on the oxygen, but we also do see that this contributor, okay, or what should I say? We should, how should I put this? The enol form does have some electron density on the carbon, okay? And so what that means, I mean, what I'm getting at here is that the alpha position at the enol is nucleophilic. Now, if we go back here, you can see that, yes, of course, this carbon is going to be nucleophilic, and we're going to talk more about that later on. But again, if you have that ketone or aldehyde existing in the enol form, and you look at the electrostatic potential map, yes, most of the electron density is on the oxygen, but there is some electron density on the alpha carbon, and that renders it nucleophilic. And of course, the title of this chapter is really, or not the title, but we talked about how in this chapter we're going to be talking about alpha carbon chemistry. And so the fact that that carbon is slightly nucleophilic is going to be very, very important to us moving forward. There, I finally said it. All right, so going back to the whole enolate thing, so I was kind of getting ahead of myself here. If you take your aldehyde or ketone, treat it with a base, you make the enolate form, well, you can imagine that the enolate is much more nucleophilic than the enol, right? That is not a surprise to anybody who's hearing the sound of my voice. You have a negative charge plopped right there on this carbon or on this oxygen, whereas the enol is an uncharged form. So enolate is going to be more nucleophilic than the enol, and we're going to see examples of enols and enolates both behaving as nucleophiles. So with that in mind, if you look at that enolate, okay, so here's the enolate drawn with the negative charge on the oxygen, and here's the enolate drawn with the negative charge on the carbon. Now, I know all of you are astute enough to look at these enolates, both resonance contributors in the blue circles, and say, well, I could have the oxygen behave as a nucleophile, as I have shown in the box on the upper left, or I could have the carbon behave as a nucleophile, as I have shown in the box on the upper right. Either one is going to work. And you might be wondering, well, what are we going to be dealing with here? Are we going to be looking at O attack or C attack? And the idea is that both can occur, okay? But it says here, enolates, as a matter of fact, generally undergo C attack, okay? Which can be drawn one of two ways, depending on which resonance form of the enolate is used. Okay, and in our chapter, in this chapter, and in our textbook, we're going to look at enolate chemistry, and we're almost always, in fact, I think we always look at C attack. Okay, that's what we're going to focus on. So it says here, enolates generally undergo C attack, and this is what we're going to focus on in our class, Chemistry 3111, like that. Now, I feel like there's a lot kind of squeezed on this page here. So I'm going to go to a blank document just for a second here. Okay, just bear with me. And I'm going to redraw an enolate for you. So let's say we have, let's even go back a step. Okay, so let's say we have a ketone. Like we'll just put acetone here. Okay, we'll draw in an alpha proton like this. And now let's say we treat it with a strong base. I mean a really strong base. I'll just put B minus, something like this. Okay, so we pull off this proton and we make an enolate. Okay, so what do we have? We draw something that looks like this. Okay, so there's our enolate. Okay, and we can draw the resonance form of our enolate, which looks like this. Okay, there we go. So we have a double bond here, and then we have our negative charge over here. Okay, so those are the two resonance forms of the enolate. And so if I draw the one on the left, so I'm going to redraw one on the left like this. This is the first enolate I drew. Now I'm going to draw the resonance form, and I'm not going to draw a resonance arrow. I'm just going to draw the resonance form. Okay, I have this resonance form where the negative charge is on the carbon. Everybody with me so far? That we've got two resonance forms of the enolate? Okay, so now it said that in our class, I keep saying almost, we're going to be exclusively looking at carbon attack, okay, where the carbon behaves as a nucleophile. So we've got two possibilities, right? We'll put an electrophile here and an electrophile here. Now I'm going to zoom in here a little bit. So there's two possibilities. You could have this mechanism where the negative charge on the carbon just attacks your electrophile like this, or you could have this mechanism where you reform this pi bond and the carbon attacks like this. Now, both of these are reasonable, okay? And these are what was drawn on the last slide. But the one of these that would be more pertinent, or the better one of the two mechanisms, would actually be this one here. And the reason why is because the negative charge is on the oxygen here, right? We know that this is going to be the more significant resonance contributor. And so therefore, this would be a more correct mechanism, or maybe I should say the better mechanism of the two. Just give me a thumbs up if that makes some sense. Both are okay, but I just want you to know that we might use both. So both of these are acceptable, but the one in the blue box, it might show up at certain times, and then the one below it might show up other times, depending on the situation. But both are reasonable, but the one in the blue box would be more accurate, okay, based off of the fact that that resonance contributor will contribute more to the hybrid. All right, that was a lot of yammering on, but I just wanted to make sure we had that down pat before we move on. So let's go back to from whence we came here. And this is where we were. So what I was just summarizing on that blank document was just this. Okay, it was just talking about that little part there. All right, so let's get back to the task at hand. It says alpha protons are the only acidic protons on an aldehyde or a ketone that can be removed to form an enolate. So here is a 4-carbonaldehyde. So you need to know how to name that. So this is butyraldehyde. Butyraldehyde, like that, or butanal, okay, or butanal. Both names are acceptable. All right, so you need to know that the alpha protons, okay, so the alpha protons are the only ones that are going to be acidic enough to be pulled off by a base, okay? This, and sometimes students will think, well, what about this proton here, the aldehydic proton? This is not acidic. Okay, so don't ever pull that thing off, okay, because you're not going to form an sp2 hybridized carbanion. The reason why the alpha protons are acidic is because you end up forming a resonance stabilized enolate. Right? If you pull off the beta or gamma protons, that doesn't happen. Okay, so we don't pull off aldehydic protons if we have an aldehyde. We don't pull off beta protons. We don't pull off gamma protons. What do we pull off? We pull off alpha protons. All right, so now that we've covered that, let's talk a little bit about how you would choose a base to form an enolate. So it gives you the pKa values of some alpha protons, and we have to consider those pKa's before we start thinking about what kind of bases would we use to deprotonate these. So let's start by looking at acetone. So acetone is a ketone. Its pKa is around 19. Acetophenone, also a ketone. Its pKa is around 18. And then you've got acetaldehyde. So these are all just pKa's of alpha protons, of ketones and aldehydes, alpha proton, alpha proton, alpha proton. So what if we got, I don't know, maybe like 17 to 19 is kind of the range here, something like that. Okay, is anywhere around there is going to be safe. So we'll say that alpha proton, pKa, put pKa 17 to 19. And again, we can play with that a little bit. Okay, it might be 16 to 20 or something like that. There we go. We have an idea. So if you're thinking, well, what could I use as a base? Remember sodium methoxide? Was that a base that we used a lot in this class, or what? Yeah, absolutely. Go all the way back to chapter 7. You know that sodium ethoxide is a strong base, strong nucleophile. But what if we used ethoxide as a base? What would we end up with then? Well, our alpha proton in this aldehyde, which is acetaldehyde, this would be our acid. The ethoxide would be our base. This would be our conjugate base, the enolate, and then ethanol would be our conjugate acid. If we look at the pKa's of the acid and the conjugate acid, the equilibrium is going to lie to the side of the weaker acid. And so if we try to use ethoxide to do our deprotonation to form our enolate, you're only going to get a little bit of the enolate, right? You're only going to form a little bit of this. Is everybody with me on that the equilibrium would lie hard to the side of the reactants here? Based on the pKa? Okay, and you see that manifest in the arrows here. They're showing you that the equilibrium lies to the side of the reactants. Okay, cool. All right, so when an alkoxide is used, the enolate, or nucleophile, can react with the ketone, which is our electrophile. So what it's saying here in the bottom is this. If you take this aldehyde and you treat it with ethoxide, you have an equilibrium, don't you? So what that means is that you still have this aldehyde. I'll draw it in black. You still get this aldehyde intact, okay? And you still have, or you have, some of the enolate as well. Let's zoom in on those. What could happen here? You've got a nucleophile and you have an electrophile. Could there be a reaction between those two? Absolutely. Absolutely. And that's kind of where we're going, okay? So this is something we're going to see in a little bit. Give me a thumbs up if that makes sense to you. We're going to have both, and so it can react, right? There's going to be a reaction between the enolate. Now, if you're looking at this and saying, Mr. Dion, that's not really proper. I thought you said that the better resonance form would be this one here, like this, and couldn't you draw it like this? Where am I? Like this? The answer is yes. Okay, you could draw it that way too. But anyhow, that's where we're going. So I'm getting ahead of the game here, but I wanted to put that bug in your ear before we move any further. So that's something that we're going to cover in section 21.3. Anyhow, so let's go back to this whole choosing a base thing. What if you wanted to convert all of your aldehyde or a ketone completely to the enolate? You want to just rip off every single proton. Well, you got a couple of possibilities then. It says, to irreversibly and completely form an enolate, a stronger base has to be used, and sodium hydride is a really strong base. Right, if you go back to your aldehyde, and we said the acetaldehyde had a pKa of 16.7. If you were to deprotonate that with a hydride, you end up producing hydrogen gas in the enolate. Well, hydrogen gas has a pKa equal to about 35. And so this is essentially going to be irreversible, right? It's going to give you complete formation of the enolate. Also, hydrogen is a gas, so it goes up the smokestack, and based on Le Chatelier's principle, it's not coming back. Now, if you're wondering, are there any other bases besides sodium hydride that I could use? Absolutely, absolutely there are. And lithium diisopropyl amide, or LDA, is a very commonly used, a very strong base that's commonly used to form enolates. Now, where do we get LDA? Can you buy LDA from a store? I mean, a chemical supplier. Obviously, you can't buy it at Target or something. It used to be by the jeans, but they removed it. Anyhow, yes, you can buy LDA, lithium diisopropyl amide, this guy right here. It can be purchased from a chemical supplier, but I'll just tell you the truth. Most chemists don't buy it. And the reason why is because it's very hygroscopic, meaning it can absorb moisture from the air really quickly. And so if you spend all your money on this, so again, this is lithium diisopropyl amide, or LDA, it usually gets destroyed over time, or it just degrades. And so a better option is to actually make it. And so LDA is usually made in the lab when it's needed. So what you do is you take diisopropylamine, that's this secondary amine, and you treat it with butyllithium. So this is butyllithium, and we abbreviate that BULI, like this butyl lithium. And so we have a carbanion that can remove the proton from diisopropylamine. Now, if you're thinking, well, diisopropylamine, come on, that's not very acidic. You're right. It's not very acidic. But if you think about an alkane, that's even less acidic. And so the equilibrium is going to lie to the side of the weaker acid, right? Because an alkane has a pK of about 50. Right, whereas an amine has a pK of around, maybe 36, 38, something like that. All right, so LDA is made this way. I don't know, or is made in the lab is what you might want to say, or something like that. But that's how we make it. In our class, you can assume that you have LDA if you need it. So you could write something out like this. You could say, well, if I take LDA and I treat my aldehyde or ketone with it, I end up completely forming the enolate. Why? Based on pKa again, right? If the ketone or aldehyde is our acid, this is our base, LDA. Then we have our conjugate base, and then the amine is our conjugate acid. Well, the pKa is much higher for this, and so this is less acidic, and therefore the equilibrium is going to lie hard to the side of the amine. So LDA is more than strong enough to remove all the protons from an alpha protons, I should say, from an aldehyde or a ketone. So if you're wondering, well, why do I use LDA? Why this base specifically? There's a good reason for that. It's because it's got these two big isopropyl groups on it, which makes it a really good base, but a terrible nucleophile. Okay, it's a terrible nucleophile because it's too sterically hindered with those two big bulky isopropyl groups. You could even make a model of it to prove it to yourself. All right, before we, in a few seconds, we're going to kind of summarize this whole base enolate thing and, kind of put a cap on it. But before we do, I want to show you another situation here. Do you remember that 1,3-dicarbonyl compound, or what I call the beta diketone, or the book called a 1,3-diketone? Anyhow, if you remember this thing here, if you look at the pKa of a 1,3-dicarbonyl and you look at the alpha protons that are in between the two carbonyls, see, maybe it's like a di-alpha. That's not a thing, by the way. But anyhow, if you look at those alpha protons, they have a really low pKa of about 9, and you can guess why. It's because you have an extra resonance contributor, don't you? If you deprotonate, you end up with all of these contributors or resonance contributors contributing to the resonance hybrid. And so because of the increased stability of the enolate, it's going to be more acidic. So based on that, you don't even need to use a strong base like butyllithium, or sorry, LDA, or sodium hydride to deprotonate a 1,3-dicarbonyl. You can even use ethoxide because the pKa is 9 of the 1,3-dicarbonyl, and the pKa of ethanol is 15.9. You can see the ethoxide makes a dandy base to deprotonate this completely, right? Again, this is our acid, this is our base, this is our conjugate base, and this is our conjugate acid. Remember, the equilibrium lies to the side of the weaker acid. And so there's no need to use sodium hydride or LDA to deprotonate a 1,3-dicarbonyl. It's overkill. It's hard to work with those reagents, so no need to do that whatsoever. Now, here's what I was getting at, is that we have a great summary here put together by the author of our textbook, which kind of covers, which situation and whether the reaction is going to be reversible or irreversible for deprotonation. So if we have a ketone or aldehyde, if we treat that with an alkoxide or hydroxide base, you're going to end up with a mixture of the ketone and the enolate, or the aldehyde and the enolate. Both are going to be present at equilibrium. If you use a strong base like sodium hydride or LDA, you get irreversible formation of the enolate complete. And so if you're wondering, do I have to know this? Yes, the answer is yes, because there's going to be situations where we only want to partially deprotonate, and there will be situations where we want to completely deprotonate. And then if you look at a 1,3-dicarbonyl, all you have to do is use hydroxide or an alkoxide base, and it's going to completely deprotonate it. LDA or sodium hydride, those are not even required. Okay, so that's kind of a summary of the end, or the last few slides of 21.1. And let's see how we would apply that with a question here. It says, draw the enolate ion that's formed when each of the following compounds is treated with sodium ethoxide. So if we're taking the first compound, for example, and we're treating it with sodium ethoxide, okay? In each case, draw all resonance structures of the enolate ion and predict whether a substantial amount of the starting ketone will be present together with the enolate at equilibrium. So it's kind of a two-part problem here. Now you see that you have two planes of symmetry here. We've got one here and one here. And so there's only one type of alpha proton in this molecule. This compound, you'd call it 1,4-cyclohexane dione. And what's going to happen is we're going to deprotonate like this, and we're going to draw the enolate that's formed, which is going to look like this. We've got our negative charge here, and we're going to draw the resonance form, which is going to look like this. So let's draw that resonance form. That's going to look like this. So you get the negative charge on the oxygen, and there you have it. All right. So my question to you is, am I going to have both the ketone and the enolate existing at equilibrium, or just the enolate? Could anybody tell me that? Will I have both, or just the ketone in this case? So in this one, I'm going to have what? So I'm going to have both. I'm going to put here both present at equilibrium. Okay, and the reason why is that this is not a 1,3 dicarbonyl. This is a 1,4 dicarbonyl. When you have both of them is when you have your carbonyls only one carbon apart, like that. But since we have two carbons in between, okay, we're going to have an appreciable amount of both. Right? We can say that the pKa of this proton is going to be somewhere between 17 and 19, right? And then we're also going to get the enolate plus ethanol. Okay, and if we go back in the notes, I always forget what our book says for the pK of ethanol. It says it's 16 or 15.9. So we'll just put pKa is equal to 16, close enough. So you're going to have an appreciable amount of both. Does that make sense to everybody? So keep in mind, this is a 1,4 dicarbonyl, not a 1,3 dicarbonyl. Okay, cool. And if you're sitting there going, that's a trick question, well, you have to look at the compound very carefully, I would say. Now, what about this compound here? If I zoom in here, this is an alpha carbon, and then this is an alpha carbon. How many alpha protons do I have in this molecule? How many alpha protons do I have? Right, the answer is one. There's one measly alpha proton, right? It's this. That's it. Okay, so I know some students said too, I'm not sure where the second one is coming from, right? Because this carbon has 1, 2, 3, 4 bonds. So it can't have a proton. So we've only got one alpha proton in this guy, and it's this alpha proton right here. So if we took this compound and we treated it with sodium ethoxide, oops, sodium ethoxide, it's all good, Audrey, don't worry about it. All right, so could practice our mechanism here, and let's draw the enolate. That aromatic ring is horrible looking. There we go, it's a little better. All right, so we end up with this enolate, and that is going to be in resonance with this form. Here we go. Oops. All right, looks something like this. There we go. Something like that. Okay, so we have these two resonance forms. And so my question is, are you going to have both present at equilibrium, or it says predict whether a substantial amount of the starting ketone will be present together with the enolate. So we're going to have a substantial amount of both, or just one for C? Yeah, the answer is we're going to have both again, aren't we? Both present at equilibrium. And the reason why is the pK of this is going to be, what was it? If we go back in here, right, we go all the way back in our notes, we said the pKa of an alpha proton on acetophenone is around 18. So we'll just scribble 18. I was going to say, 16 or 17 to 19, which would have been right in the sweet spot. We'll just say it's around 18-ish, okay? And then if we put plus ethanol, it has a pKa that's around 16. So you're going to have both. You're going to have both present there. All right? So remember, the only time you're going to get one or the other, the only time you're going to get complete deprotonation with sodium ethoxide is if you have a 1,3 dicarbonyl. Okay? So let's say if we took this compound and we treated it with sodium ethoxide, that is going to completely give us the enolate. So if we draw it like this, okay, that's going to go completely in one direction like that. But all of these are going to be in equilibrium. So maybe I should put equilibrium arrows here. There we go. Fixed it. All right, good. So let's move on from there. We're going to cover one more section before we take another break. And this section deals with alpha halogenation. So again, we have our ketone here. So this is cyclohexanone. Okay, it's got two alpha carbons in it. Anyhow, we're just going to focus on one for now. And it says here that under acidic conditions, ketones and aldehydes can undergo alpha halogenation. So that means we can install a halogen, like a bromine, at the alpha group, at the alpha position. Keep in mind that these square brackets mean acid catalyst. That's what square brackets represent here. So acid catalyst, bromine, and we end up with alpha bromination, and we produce HBr. Now keep in mind, it says this reaction works with chlorine, bromine, and iodine, but not with fluorine. So if we're in acidic conditions, right, we're in a catalytic amount of acid. If we're in a catalytic amount of acid, okay, it means we're going to have an enol in there, aren't we, right? We're going to have the enol because we're going to have tautomerization occurring. So here's the mechanism of this reaction. The first step is something that we've already seen, okay? Previous slide, right? I told you that you had to know this mechanism a while ago. I said you get the proton transfer, you draw the two resonance forms, you do another proton transfer, and you form your enol. So this is your enol form. But now that enol can act as a nucleophile in the presence of Br2, of bromine. After it does a nucleophilic attack, we do a proton transfer, and we end up with our alpha bromo ketone. So I think it's worth knowing this mechanism as well. So you have to know the first part, and I want you to know the second part of the mechanism as well. All right, there we go. Let me see. No, that's good. All right, well, let's move on from there. Let's talk a little bit more about this alpha halogenation thing. What if you have an unsymmetrical ketone? Well, in that case, the halogen is going to end up being added to the more substituted carbon. There's a good reason for that. It's because since you pass through an enol, well, if you had two enols, like these two regioisomers, which one is going to be more stable? The one that's more substituted would be more stable, and so the bromination would occur at the alpha carbon there. Nothing really surprising there because we've talked about substitution on alkenes before, and we said the more substituents we have, the more stable it is. It says here, alpha halogenation provides a two-step synthesis for the synthesis of an alpha beta unsaturated ketone. So in the first step, we do our alpha halogenation. So again, the first step is catalytic amount of acid and bromine. That's our alpha halogenation. And that would end up forming, there's not a lot of room here, but that would make this as your intermediate. Okay. And then in the second step, you treat that with a base like pyridine. And so what's going to happen then? So let's say you have pyridine. I don't really have a lot of room to draw this, do I? So let's say you have your base, which is pyridine here. I don't even think this mechanism is in the book, okay? It's going to rip off this proton from the double bond, lose the leaving group, and that's how you end up with what we call an alpha beta unsaturated carbonyl, or an alpha beta unsaturated ketone in this case. Now, besides pyridine, you can use pyridine as your base, or you can use potassium T-butoxide, or you can use lithium carbonate. When was the last time you heard of lithium carbonate, right? Any one of these bases will deprotonate at the alpha position to make your alpha beta unsaturated ketone or aldehyde. So there you go. We've covered alpha halogenation, and now we've covered a way to make an alpha beta unsaturated ketone. If you're wondering, why would I even want to make this? Well, that will become more abundantly clear next class when we look at something called Michael addition or conjugate addition. So we'll get into that later on. Anyhow, a couple more reactions to cover before we wrap up section 21.2. The next one is a great name reaction. Three names, all of them kind of cool. You get the Volhard-Zielinski reaction, which we affectionately know as the HVZ reaction, okay? If you're wondering, with this treatment of, aqueous acid and bromine, could I do an alpha bromination on a carboxylic acid? And the answer is no. You can't use these conditions, okay? These conditions to brominate at the alpha position of a carboxylic acid because it doesn't exist with the enol form. And so what we do is we use the HVZ reaction to allow us to put in a halogen at the alpha position. And it's a two-step process. The mechanism is kind of partially written here. It's kind of like a proposed mechanism. The first step is to treat it with bromine and phosphorus tribromide. So PBr3 is phosphorus tribromide. And that's just a covalent compound. So I know you knew how to name that, but anyhow. So we have bromine and phosphorus tribromide. And what that does is it ends up forming this out. So you end up with this point, okay? This is just the first step. You get to this point. You'd call this an alpha halo acid halide is what I would call that, okay? Because you have a halogen here and then you have an acid halide. And then you treat that with water and that removes the bromine from the acid bromide in this case, or it just hydrolyzes it essentially, and you end up with an alpha bromo carboxylic acid, which is what we have on the far left. So again, I'm not going to ask you anything about this mechanism whatsoever. I will not ask you about the acid halide enol intermediate or anything. I just ask you to know the reaction. And what's neat about the HVZ reaction is it actually comes up in chapter 23, I think, or something like that. We actually look at these intermediates to make amino acids. So amino acid synthesis. It's not covered in this chapter, but it's something that we will look at later on. So the HVZ reaction, again, 2 steps. First step, bromine and phosphorus tribromide. That makes the intermediate shown in the red box. I'd call that an alpha halo acid. And then you treat that with water and it hydrolyzes the acid halide and you end up with an alpha halo carboxylic acid. In this case, it's an alpha bromo carboxylic acid. There you go, HVZ, 3 people it took to develop that thing. It says here alpha halogenation can also be achieved not only under acidic conditions, but under basic conditions. So if you were to take this compound, so this would be 2,2-dimethyl cyclohexanone, you can see that it's got 2 alpha protons, doesn't it? Right? If you treated that with sodium hydroxide, you can rip off one of those alpha protons, and then you can do a bromination, so just a nucleophilic attack, loss of leaving group here, and you end up with a bromine in the alpha position. So this is alpha bromination under basic conditions. Well, what's interesting about that is that once you make this intermediate, and I'm just going to draw what was on the previous slide. Okay, on the previous slide, you saw that this was the first product. Well, now the second alpha halogen, or sorry, the second alpha proton is even more acidic because you've got this dipole going this way, but you've also got a dipole because of the electron withdrawing effect of the halogen. So that means that the second deprotonation / halogenation is going to occur even faster. So it's kind of like a runaway train. It keeps halogenating and halogenating until it's really just exhaustive. Like it just keeps on going. So you can see that we have 2 bromines installed at the alpha position. And where this becomes really relevant for us is what if you have a methyl ketone? If we have a methyl ketone, so a methyl ketone, and this is a methyl ketone, right? You're with me that this is a methyl group. Well, the methyl group, if I redraw this compound, okay, so if I redraw this ketone, that methyl group has 1, 2, 3 alpha protons. And so what's going to happen is you're going to keep ripping those alpha protons off over and over and over. Let's switch over to a blank document here, and I'll kind of go over this with you. So let's say we have that compound again. I'll redraw it here. Okay, we've got a total of 1, 2, 3 alpha protons. So what's going to happen first is the hydroxide is going to rip off one of those protons. Okay, so I'll just draw the enolate like this. Okay, of course, there's the other resonance form. I'm not going to bother drawing it right now. And then what's going to happen is this is going to react with bromine, Br2. So we get nucleophilic attack, loss of leaving group like this, and we add a bromine. So now we've brominated once. But remember, we still have 2 more acidic protons, and these are even more acidic than they were before now that you have that bromine in there. So now another hydroxide ion is going to do another deprotonation. So it's going to remove a proton, and you're going to end up with another enolate. So now you end up with this enolate. We have the negative charge. That's not very pretty. Let me fix that up. There we go. Negative charge here, and it's going to do it again. Okay, so it's going to react with bromine. So we have nucleophilic attack, loss of leaving group. I'm leaving out some lone pairs here. I'm aware of that. I'm just doing this for instructional purposes only. So now you've got 1, 2 bromines. And now the third proton is even more acidic. So you can see where I'm going. You keep moving with this, and eventually you're going to end up with this, where you have that carbon has 3 bromines attached to it like this. And you're still in base. And so now what happens in the next step is that the base is going to act as a nucleophile, and you're going to form a tetrahedral intermediate. So check this out. Now that you've formed this tetrahedral intermediate, you've got to decide, if I reform the carbonyl, what am I going to lose as a leaving group? Am I going to lose the hydroxide, or am I going to lose CBr3? And you might remember from the previous chapter, we said we don't lose any carbons with a negative charge. And I said there are some exceptions. This would be an exception to that rule. I'm going to use my blue arrows. You actually can lose, you're going to lose minus CBr3 minus. Now, why can you lose that as a leaving group and reform this carboxylic acid? Okay, why can you do that? Why is this a good leaving group? This is a good leaving group because let's think about it. You've got a carbon with a negative charge, but you've got 1, 2, 3 electron withdrawing groups, just yanking electron density away like crazy. And so that is why CBr3 minus is actually a good leaving group. So this is an exception to the rule. Now, if you're very astute, and I know you all are, you're probably like, you know what, Mr. Dion, this mechanism, it ain't over till it's over. And you're still in base, man. So if you're in base, that means that the hydroxide is going to rip the acidic proton off after you lose the CBr3 ion, and you're going to form a carboxylate. And I'd say you're absolutely right. Okay, so we form a carboxylate. And so that means you need to do one more step. And in the last step, you're going to treat it with aqueous acid, and that's going to give you the carboxylic acid, like that. And so what did we do? We took, it's a long mechanism, but we took a methyl ketone. So overall, we took a methyl ketone. I'll just draw it here so you can see the overall mechanism. We treated it with sodium hydroxide and bromine, followed by treatment with H3O plus in the last step, and it made a carboxylic acid out of our methyl ketone. This is called the haloform reaction. Haloform reaction. All right. And actually, I wrote this incorrect. What's doing the deprotonation here, sorry, I made a mistake. It's actually not hydroxide. It's the CBr3 minus ion. I was getting ahead of myself. Is doing the deprotonation here. So you end up forming the final product, but you end up with CHBr3. And this is called bromoform. Bromoform. So if you have CHCl3, you call that chloroform. If you have CHI3, you call that iodoform. And so that's why we call this the haloform reaction. So what is it again? It's the conversion of a methyl ketone to a carboxylic acid. If you're wondering, man, he's been parking here on this thing for a long time. Why? Because this is an extremely important reaction in organic chemistry. And the author of our textbook and the author of our quizzes love to use this reaction. Okay, so there you go. The haloform reaction. Give me a thumbs up if you're with me 65% of the way or greater on the haloform reaction. I really took a lot of time to go over this, but it is such an important reaction in organic chemistry. So let's go back and I'll show you what I had in my notes about the haloform reaction, which is right over here. Okay, so I said the haloform reaction converts a methyl ketone to a carboxylic acid. Very, very important reaction. I think you should know that mechanism. There's a lot of repetition in it like this. And I explained why you can lose CBr3, why this can be a good leaving group, right? And then I showed you where I made the mistake was this part here, which is shown correct here. So you end up forming bromoform. So if you're wondering what the pKa of the bromoform, I just have it scribbled in here in my notes. The pKa of a carboxylic acid is around 5, and the pKa of bromoform is around 14, something like that. So the equilibrium is going to lie hard to the side of the weaker acid. And there you go. So this reaction, like I said, works well with chlorine, bromine, and iodine. So chlorine produces chloroform, bromine produces bromoform, and iodine produces iodoform. Anyhow, this reaction, the haliform reaction, works the best if the other carbon has no alpha protons on it. Otherwise, you can get mixtures, which is kind of a crummy thing. But anyhow, there you go. That's the whole reaction, just like that. And so here in question 21.8, it asks us to predict the major product for each of the following transformations. Well, good thing there's only one here. And then propose a mechanism for its formation. So if we remember that what happens in this reaction, in the first step, we do an alpha halogenation. So we install a halogen like this. And after the second step, we do a deprotonation, and that gives us an alpha beta unsaturated ketone. So it would make this compound here. So let's draw the mechanism. So remember that it's going to pass through an enol if we're in a catalytic amount of acid. So let's start by drawing our hydronium ion out, our beautiful hydronium ion, and we're going to do a proton transfer in the first step. So there we go. Oops. All right, so let's draw the oxonium ion, which looks something like this. There we go, like that. And now water is going to come in and act as a base, and it's going to abstract one of the alpha protons. I'll just draw it in, of course, for instructional purposes. There we go. And so I'm going to rip off that proton, and then I'm going to form my double bond here and restore neutrality to the oxygen. So let's draw the product. That, and there we have it. There is our enol. Good. So now that we've got our enol, the enol can react with bromine. So we'll put it in the presence of Br2 like this. And so we're going to do a nucleophilic attack like this. And so now we've got our bromine attached to this, and we have a positive charge on our oxygen. So there's our bromine like this. And now water can come in as a base. I'm kind of running out of space here. The water is going to come in and act as a base. It's going to restore neutrality here. So we end up with the compound that I had written in blue. And then just to shorten it, since I'm running out of space, I'll just write pyridine, which is our base. So I'll draw the structure of pyridine, and pyridine will abstract, let me draw my proton here. It's going to abstract a proton like this, make the double bond, we lose the bromine, and there we go. So maybe I'll put this compound in black since this is our final product. And there you go, that's the mechanism for the whole thing. So first we form the enol, then we add the alpha halogen, and then we do the beta elimination to form the double bond between the alpha and beta carbon. All right, let's try another one here. This is question 21.9. Identify reagents that can be used to accomplish each of the following transformations. So we're starting with cyclohexanol, and then we're making cyclohexanone, or alpha, what would you call this? You'd call this a 2,3 cyclohexenone, I guess. Anyhow, so we know that we can make this compound. Right? We can make this from the alpha halogen, right, like that, and then we can just treat it with a base like lithium carbonate or potassium T-butoxide. And so then the question becomes, well, how do I get from here to here? Well, you would first want to have cyclohexanone and then just do an alpha halogenation, right? So the first thing we're going to do is we're going to oxidize the cyclohexanone, and for that we can use PCC, or we could use Swern or Des-Martin, what have you. I'll just use PCC, and that would make the compound in red. Then we're going to do our alpha halogenation. So for that, we're going to use a catalytic amount of acid in bromine. And then the last step is the elimination. And for that, we can use pyridine, or we could use lithium carbonate, or we could use potassium terbutoxide. Either one is good. Same thing here. Right, it's very much the same rationale here. We want to make this aldehyde, this alpha beta unsaturated aldehyde, and we could make that from this alpha bromoaldehyde, and we could make that, of course, from the aldehyde. So from this aldehyde. And so the question becomes, well, how do I get from here to here? Well, you can see that all we have to do is oxidize that to an aldehyde. So again, you would use similar conditions. You'd use PCC to make the compound in blue, the aldehyde, then you install the bromine at the alpha position. So I think this is the exact same conditions as before, isn't it? So aqueous acid and bromine. And then in the third step, let's just choose a different base for fun. We'll choose potassium T-butoxide, okay, as our hindered base. And there you have it. So both of these are identical. All right, there's no difference between either of these. Question 21.10, predict the major product. Does anybody remember the name of this reaction where we have bromine and phosphorus tribromide in the first step and then water in the second step? It's got a tsatzy name. You can just give me the acronym if you want. Anyone? Yeah, thanks, Tiana. This is the HVZ reaction, the Hell-Volhard-Zelinsky. So what that does is it makes an alpha bromo carboxylic acid, so you end up with a bromine in this position. Oops, sorry, the alpha bromo haloacid in the first step. So I'm just drawing the intermediate here just for fun. And then in the second step, we hydrolyze the acid halide and we end up with carboxyl group. Like that. And that's it. All right, so Hell-Volhard-Zelinsky reaction. So I'll scribble that down since this is an important reaction. Hell-Volhard President Zelinsky reaction. All right, and then the next one, 20.11. Oh man, I got a lot of problems in here. 20.11, identify the reagents that could be used to accomplish each of the following transformations. You're also going to need reactions from previous chapters. Why don't we save this one for next class? So why don't we save this for Friday? So I'm going to put here Friday, it's Friday. And we'll try this one then. I want you to give it a shot. And yeah, you can see you'd use the Hell-Volhard-Zelinsky. And this one, this one you'd use the Hell-Volhard-Zelinsky. And this one you'd also use it. Yeah, this reaction is everywhere. All right. The next one is predict the major product when each of the following compounds is treated with bromine together with sodium hydroxide, followed by aqueous acid. Well, this one's pretty fast. This is just the haloform reaction. Right. So in step one, we treat it with sodium hydroxide with bromine. And what that actually gives you is this. You would end up with the carboxylate plus CHBr3, right? And then in the second step, you treat it with aqueous acid, and that protonates to give you benzoic acid. I'll just write the condensed structure like that. So this is the haloform reaction. All right, and remember this is called bromoform. Okay, man, I gotta keep going here. Let's see. After this, we'll take a short break. It says, identify the reagents that you could use to accomplish each of the following transformations. You will need reactions from previous chapters. Well, that's a cue. Why don't we save this one for Friday as well? Come back on Friday and we'll tackle this one. That'll give you a chance to give it a try. You can see that you could make this Fischer esterification, and you could use the haloform reaction here. This one you have an imine, so you can hydrolyze that to a carbonyl, make a carboxylic acid, acid chloride, and then a primary amide. Anyhow, just kind of talking through those. So why don't we take a short break before we come back and we cover what are called aldol addition reactions.